take care of your examples. It's impossible to finish at least mathematical physics course. So anyway, can you speak again a little bit louder?
So I was saying हमारे लिए भी impossible है हमारे पास तो 10 एक्स्ट्रा दिन है
हाँ नहीं, पर मैं ये जानना चाह रहा था कि बाकी टीचर्स के कोर्सेज कैसे फिनिश हो गए, मतलब आई कुडंट फिगर आउट। नो आप
कंप्लीट नहीं
नहीं
हुआ
सर
है।
सेट।
टॉपिक्स कटे हैं हमारे दो
अच्छा, थोड़ा पीस
टॉपिक्स जो
करना है।
एग्जाम में नहीं आते
राइट। नहीं, आपका कहना सही है कि आप लोगों के लिए भी टफ है, लेकिन अगर आप दिल्ली यूनिवर्सिटी का एमएससी के लेवल पे मैथमेटिकल फिजिक्स का सिलेबस देखेंगे, इट इज एक्सपेक्टिंग दैट वी आर गोइंग डूइंग रिव्यूज ऑफ लॉट ऑफ थिंग, बट वी आर नॉट डूइंग दैट। टू बी ऑनेस्ट, वी आर एक्चुअली डूइंग एवरीथिंग। आई मीन इट्स नॉट एक्सपेक्टेड कि मतलब कोई भी चीज ऐसी नहीं थी जिसमें कि मैं ये कह सकूं कि अरे आपने किया हुआ है, अदर देन कॉम्प्लेक्स एनालिसिस का शुरू का पार्ट। So there lies the major difficulty in this particular portion, because mathematical physics is mostly applied. Anyway, it doesn't matter as long as you understand and as long as you understand the basics. So, is screen visible?
यस सर
सर
Good, thank you. So this is what is the summary of previous class. We did something on the continuous groups. Basically, these four major classes: ON, SON, UN, and SUN. And as you can see, what I have written on this page, it is mainly what we did yesterday. So ON is n cross n orthogonal matrices in real space, n cross n or n space, determinant having plus minus 1, property of the orthogonal matrices. Order of these ON group turns out to be n into n minus 1 over 2, and in general it represents rotation and reflections in real space. SON with this special that the determinant is equal to plus 1, so we are choosing that to be plus 1. Other than that, it is basically the subgroup of ON, and it corresponds to real rotations. So rotation only. Sometimes you will find out books are writing proper rotation group. And then we just extended the same terminology in complex plane, and we said that we have something called UN and SUN. Here, the only, I mean, I would just like to emphasize the only major difference between the two, that SUN will have order which is one less than the order of UN, because we are going to choose one determinant condition plus 1 for SUN out of EI theta, which is infinitely possible conditions which were there. Okay, so undo. Where is my undo? Doing all kind of things now. Yeah, good. And I asked you, make sure that you work out the most general form of SO2 and SU2 matrices. So remember, SO2 has 4 components, and we discussed that certain components are constrained. So you should be left ultimately with only one independent parameter or the element. In the case of SU2, you have 8 of these n square, because they are the complex entries in the 2 by 2 matrices. And then you will continue to put constraints there. So there you should be able to reduce it from 2n square minus n square, which is n square, minus 1. The one constraint will come from the determinant. So that means for 2 into 2 matrices, you will get 3 independent elements. So please work it out. Write down the just most general form, and in case if you face problem, just come back. Now today I am just going to emphasize, since we are left with 2 classes, so just emphasize something on this kind of a group which we call as the Lie group, after the famous Sophus Lie, who basically worked on the continuous groups. And the idea is this, that in case if the group elements, if the group elements depend continuously on parameter, one parameter or parameters that vary over closed interval. So the word is continuously, parameter, closed interval. Remember the matrix which we wrote, r theta, cos theta, sin theta, minus sin theta, cos theta. Rotation matrix in 2 into 2 space or two dimensional real space. Here theta is a continuously varying parameter and the value theta can take is bounded. It is over the closed interval. So under the composition, it forms a group. So Lie group, they correspond to all such classes. So for example, this SO2, and in general we can generalize it to any SON, and also for SU2 to SUN. So basically Lie group will correspond to doing certain things with the groups which are continuous in nature and which depend on the parameters that vary over the closed interval. So it is basically studying certain continuous groups. Okay, the continuous groups which are important, I mean, since SON and SUN, as I will say soon, you will see that it will correspond to our orbital angular momentum and spin angular momentum operators. Okay, now what is the basic idea? The basic idea is simple in this. So what it says that if you have a group of these kinds, which means the continuous group of the kind which I have written on the top, then a group element or operation through a finite parameter, and I will of course emphasize what I am going to write. So don't worry about it. Let me just finish writing this. It can be obtained. So group element can be obtained by performing infinitesimal operations repeatedly about identity. Okay, identity element. Now, what I am trying to write, remember that Lie group is going to study certain continuous groups. Particularly, we have in mind is SON, SUN kind of groups. Idea is that in these groups, if there is a finite rotation theta, then I can think about that this finite rotation theta can be obtained by having infinitesimal thetas, plenty of those thetas applied one after another. So infinitesimal operations repeatedly about the identity element. So this is the idea that we will be able to achieve any finite theta by continuously varying this delta theta infinitesimally. That means the very small value many times. So this is the basic start of the Lie group, where we start by writing, so this is the general one, that any arbitrary element and delta alpha, so alpha being the parameter of the group, which of course theta as for the rotation, but since I want to write the generalized one, so just take alpha to be the parameter. Identity. Now, do you remember what identity element corresponds to in the case of rotation group? It corresponds to what value of theta?
0.
So this identity element basically corresponds to value of alpha equal to 0. This is what the identity element is about. Plus, now this is the interesting portion, I delta alpha s. So this is the concept or the idea what I have written there is now basically expressed in mathematical expression. Delta alpha is nothing but the infinitesimal operation, and S is called the generator the word generator of this infinitesimal operation operator. So what am I talking about? Let's just think about it conceptually. If I want to think about any finite theta, so if you want to think about it, you can always build very small delta thetas, and you can see that you can reach the finite theta by applying this delta theta repeatedly. So there are the delta theta and you apply it repeatedly and you will find this element theta. So this u delta alpha, which is the group element for the infinitesimal element, which is generated by this generator S. So generator generates the infinitesimal operation around the identity element. The reason why I is chosen, I mean, several books even don't write I, but I will tell you later why I have chosen I here. And several books, of course, use it. There is a reason for using it. I will come to that soon. But this is the basic concept. I mean, the concept wise, it is rather simple. Since it's a continuous group, so I can think about it in terms of the infinitesimal operation. And this idea is what is important, because this idea has few things. First, I can just think about any finite rotation as the successive operations of the infinitesimal ones. Okay, so I can generate anything out of the infinitesimal. Second, it comes up with the concept of the generator, that there exists some generator which generates these infinitesimal operations. So S is the generator of this infinitesimal operation. That means in the case of SO2, which is the rotation matrix, there exists some generator of this infinitesimal rotation. And hence you will see that in these cases that the number of generators which you will get in any Lie group, this will be equal to the order of the group. So if there are three angles, then there will be three generators. If there is one angle, then there is one generator. So Lie ultimately tried to write down this because what he did later, that generators themselves make their own vector spaces, generators themselves have their own generator algebra, and you can understand all the things related with this group U delta alpha just by studying the properties of these generators. So the concept once started, it goes to the point that these generators play important and very important role in determining that group structure. Okay, so question only up to this point and then I will go further. Okay, so let me just apply it and then you will try to understand it. Wherever you have questions, of course you will have. So these are minimal set of quantities that can be used to describe our group element. So let me just continue. So what do we say? If I want to achieve any finite any finite parameter. So now I am expressing my group U is the function of any finite parameter. What does this idea say? I should be applying this U of delta alpha many times, right? So I can just think about dividing my theta into n of those steps, let's say, and I will say theta by n step I will apply first, then I will apply next theta by n, then I will apply next theta by n, and if I apply it n times, then I should reach to this theta. So let me just write down I plus S, I plus I alpha n S, and this is applied n times. In fact, I can write down that this infinitesimal should be as small as possible. So limit n tends to infinity, I plus. So you multiply these n times and then you just take limit n tends to infinity, which means that our alpha by n is a very small quantity or the infinitesimal operation. Now, do you see where we are going? If I write U alpha, which is a group element for any finite operation, this is written as limit n tends to infinity I plus small I alpha s over n raised to power n. What kind of a structure do you get? Limit n tends to infinity, identity plus this.
It's exponential of
Exponential of what?
so
I
I alpha s over n.
alpha, no, not n, because this is the property I, so I plus lambda over n raised to power n is exponential lambda. So this is just this. So interesting that if I start with this infinitesimal operation, infinitesimal group element, I apply it n times, in the limit n tends to infinity, this will become e raised to power I alpha s. In fact, this gives you a relation between the group element and the generator s. So if I ask you to write down, for example, s, so what will be s which will come out from this? So if I want to write s in terms of u alpha, instead of writing u alpha in terms of exponential I alpha s, if I want to write s in terms of u alpha, so how should I write?
Log of u alpha over I.
So there is possibility that you can do log, or there is a possibility that you do this du by d alpha. What will be the result of du by d alpha?
Alpha e power I alpha.
Right, and then put alpha equal to 0. So let me just write it down. So this will become s will become minus I, you just do that, du over d alpha, alpha equal to 0, where u is e I alpha s. Now essentially what I am saying is this, or what Lee said is this: just by understanding this generator, which is nothing but the infinitesimal group element about this alpha, du over d alpha about alpha equal to 0, that is the small gradient about alpha, yeah, d of d alpha of u. Just by studying this generator, you can get the full group. That means you can understand any group element. Remember this u alpha. So this is the basic idea behind the Lie groups, or understanding continuous groups through Lie group formalism. That we are going to study continuous groups by studying its generators, and the job of the generator is to generate this infinitesimal operation of that parameter. Now, up to this point, it looks abstract. But what is clear from this point is that I can just first find out S, and if I find out S, then I have found out my U. Or I can find out my U, and if I find out my U, then I can find out S. But the interesting thing is that the group elements, they are generated by these generators. So if you know your generator, you can basically get the group element U alpha. And if you know your group element, you can actually get your generator also from that. So we are going to do something about this, and we are going to do it from two different formalism just to emphasize how this thing works. So I will do SO2 first, and there I will use one formalism, then I will use SO3, then I will use another formalism, and we will just see that these are the two different approaches of studying it. But what we will get in a sense afterwards, you will see that it gives you the beautiful physics from it. Okay, so let's start with this idea. Let's just do what I have said. So I study SO2. Fine. There we are doing, in fact, not U. SO2 is in the real space, or is it in the unitary space, complex space? SO2.
Real
Real
space.
space. So we were using this R. So if I write R of delta theta, this will be what? I plus delta theta times some generator of this. So now I have to figure out what is the generator of this SO2. How many generators should I get in this? One or many? What is the order of SO2?
What?
One. So how
Yeah.
many generators should I get? I should just think about one generator. Can you think about what kind of matrix structure it will have? What is the matrix structure of R delta theta, SO2? What kind of matrix we are talking about?
2 cross 2.
2 cross 2.
Yeah, this is 2 cross 2. This is the 2, right? So identity is 2 cross 2 identity. Delta theta is just a number. I is of course I root minus 1. So S will be what? 2 cross 2 matrix. Yeah, I mean, this is what we are interested in figuring out. Matrix. Yeah. So what will be R theta? Given R delta theta is equal to this. So apply it n times, limit n tends to infinity. What will be the result?
Exponential of I delta.
Exponential of I
Theta S.
theta s, right? So it is just that. I mean, this is just the direct application. We haven't done anything. To be honest, up to this point, all I have done is first I wrote the generalized structure, and now I am coming to, let's say, specific SO2 example. I'm just doing the proof of the principle. You already know several things about R theta, but I can also think about writing it like theta S prime, where S prime is related with IS through IS. Yeah. And S prime, since it is just by I times S, so it is also a 2 by 2 matrix. Now, can I say something about S prime is the first question. What kind of group element R theta is? So in this case, what am I doing is, I am going to study the properties of this S prime just by knowing the structure of R theta. So that is my first formalism. What kind of matrix R theta is representing? It is SO2 group. What kind of 2 by 2 matrices?
Cos theta, sin theta minus.
Yeah, but these enjoy what O property? Orthogonal. Now,
Determinant.
orthogonal is nothing but RT is equal to R minus 1, right? So let's just find out what is RT and let's just find out R inverse and just equate it. So what will be R of T? What will be this in terms of this guy? E theta and RT.
So transpose of S prime.
S prime T, right? This is absolutely fine. What will be R inverse? That will be E
minus
minus
theta.
theta S prime. So what do you get out of this? S prime T is equal to S prime T is equal to
Minus S.
minus S
Minus S.
prime. What kind of matrix S prime would be? Which is having this property, matrix transpose is equal to minus of this is
Q symmetry.
excellent. So we already know that the matrices we are going to talk about are skew symmetric. So just by knowing the property of these orthogonal matrices, I can immediately say that this S prime is nothing but skew symmetric. Can you also tell me what kind of matrix S will be? If S prime is skew symmetric,
Skew.
okay, I will come to that. I will soon come to that, but let's just so reserve the question.
Is symmetric matrix.
Which one is symmetric?
So
S.
S.
Oh, okay. I mean, S. I am going to raise this point again. So let me just write down questions. So you will ask me again. What kind of matrix S is, yeah, where we already know the relation S prime is equal to IS. Yeah, we'll come to this. But SO2 also enjoys another property of the determinants. So orthogonal you have already studied. What was this property of the determinant? S special. That determinant
+1 determinant.
of R theta is +1. Now, without going into the detail, I can tell you that determinant, whenever the matrices are given, then the determinant of R theta can be written as E of theta trace S prime. Of course, it can be shown. I am just avoiding that for the time being since I want to emphasize on the concept. So, determinant of R theta is equal to E theta trace S prime. And this guy has become what? Zoomed. You are still able to see it or no?
Clear,
Yes,
sir.
sir, we can see.
Okay, let's see if it gets zoomed. Now, what kind of zoom is this? Oh, bad. Okay, I hope you are able to see. I'm so sorry. Yeah, so what kind of now that the determinant of R theta is equal to +1 and knowing the relation that determinant R theta is given by E of theta trace S prime, what will you say about the trace of S prime?
Sir, 0.
0.
Trace of S prime will be 0. So now you know two things about S prime. Just by knowing that you are studying SO2, orthogonal 2 by 2 matrices and determinant 1. So it is a 2 by 2 matrix. It is orthogonal condition is satisfied. Determinant is +1. You find out that it is S prime has to be 2 cross 2. Traceless. Trace of S prime is 0. Skew Hermitian. Oh, sorry, skew symmetric. Since we are still talking about the real space, skew symmetric. S prime. So can you now think about not any, the most general 2 by 2 traceless skew symmetric matrix? Can you just build it for me on the basis of just these three conditions? So it has to be 2 cross 2. Okay. It has to be traceless, skew symmetric. What property skew symmetric will enjoy? Diagonal.
Diagonal elements are 0.
Diagonal elements can only be 0. And if I have to now think about the off diagonal, one of them will be independent, right? And what will be the most general, most basic, from which all other skew symmetric matrices can be made? That will be 1 minus. As soon as you wrote 1, it becomes -1. And any other skew symmetric matrix can be built just out of this 1 minus 1. The structure of S prime is clear, or the structure of this generator is clear just by knowing the properties of the group R theta, which is that it is a special orthogonal 2 by 2 matrix. Any other real number if you want to put, please look into it. That is nothing but some sort of order of this. So you can generate all other elements or all other skew symmetric matrices from this one. And this is the only most generic 2 by 2 traceless skew symmetric matrix. Now, this is the first important part, that in the case of Lie group, knowing the group structure can help you figuring out the structure of your generator. Yeah, but I wrote it in terms of S. So let me just try to write down the same thing in terms of S. How can I write in terms of S?
Minus IS prime.
Okay, great. Minus I S prime. And what will be this structure? So 0. Next element.
Minus iota.
Minus I.
Minus iota. Iota.
Iota.
0.
0.
Can you identify this matrix by the way? 0, 0, minus I.
Poly.
This is sigma 2. It is exactly the second polyspin matrix, or sometimes you write it sigma y, which has this I coming in. This is the reason why I actually introduced I to begin with, because now you see certain structures of this. First, okay, come back. What will be the kind of matrix S is if S prime is symmetric? That is easy, right? I mean, you can do something quickly. You know polyspin matrices now.
Symmetric.
Yeah, but it also has now I's. So it will be
Permission.
Hermitian.
right. So this guy will be Hermitian. This guy is 2 cross 2 and this guy is traceless. So the reason why we introduce I in the first place in this case of identity plus, look at this small I which I use there. It is just to bring back our Hermitian knowledge into it, nothing beyond that. Since we know that we played with Hermitian matrices a lot, and Hermitian matrices allow you to just move back and forth between, let's say, real and the complex space. So this I is giving you that power directly, even in the real space, right? I mean, even in the real space, you are basically using something called Hermitian. So S is a Hermitian 2 cross 2 traceless matrix. What was this S? This is the generator of
R
SOP.
theta.
right. So R theta. Now I can just write it down as E I theta sigma 2, where sigma 2 is 2 cross 2 traceless Hermitian matrix. And I can tell you that lot of properties related with groups can just be found just by knowing what we can do with this. For example, we never wrote anything like r theta is equal to cos theta sine theta minus sine theta cos theta. This is the structure which we remember about r theta. It doesn't look like this structure, right? It looks like r theta is equal to exponential I theta sigma 2. Can I get this structure from this? What we have got? Can we get that?
We would have to diagonalize the R theta.
Okay, no, you do not need to. Remember, r theta is currently written as
Differentiate.
you do not even need to right now differentiate, because you have already got sigma 2. You are going to use the property of sigma 2 square. What is the property of all sigma matrices, polyspin matrices? Sigma 1 is square, sigma 2 is square, sigma 3 is square, all of them. So you can do that. Okay, I mean, you just multiply 1, 0 minus I 0. It turns out to be not exactly 1, it will turn out to be I, right? I mean 2 cross 2 identity matrix, right?
Yes, sir.
Yeah, I mean
Yes,
you can
Yes,
check
sir.
it. By the way, please remember
Yes.
that. I mean polyspin matrices, they are very, very useful and very interesting also. But let's just continue. Okay, if I know that, so I can expand my exponential I theta sigma 2, right? So how can I expand in terms of the series? I plus I theta sigma 2 plus I theta sigma 2 square over 2 factorial plus I theta sigma 2 cube over 3 factorial, so on and so forth. You can always do that, right? And just collect the terms, even terms and odd terms. So even terms, first I theta sigma 2 is square over 2 factorial. What will be the next term here? I theta sigma 2 even
Four.
terms, 4
4.
over 4 factorial,
4
so on and so
factorial.
forth. And here I theta sigma 2 first term plus I theta sigma 2 cube over 3 factorial, so on and so forth. So now use these property, the property which I have already given you. So sigma squares, sigma 2 raised to power 4, they will all be nothing but an identity matrices. So what will be this becoming? I plus next one term.
I by
I
2
by
factor
2 factorial.
So I square, what is I square?
I
minus 1.
minus 1.
Minus theta square I over 2 factorial. What is the next term? I raised to power 4
Plus theta.
plus, okay, plus theta 4 I over 4 factorial, and then you will find out terms like this. Let's just do something here also similar. I theta sigma 2, what will be the next term? I cube
minus I.
minus I, excellent. Theta cube, and what about sigma 2 cube?
Sigma 2.
It will be nothing but sigma 2. Remember, sigma 2 square is identity, so you just sigma 2 cube, and this will be 3 factorial, and you will find out terms like this. So what is my first term? 1 minus theta square over 2 factorial I plus theta 4 over 4 factorial I minus so on and so forth. So I can just take my identity outside, and what am I left with? 1 minus theta square over 2 factorial plus theta 4 over 4 factorial, so on and so forth. What is this series expansion?
Cosine theta.
Cosine theta. Right. Now, see, I take I theta sigma 2 outside. Yeah. Then what am I left with? 1 minus not 1. So actually, I should take just I sigma 2 outside. So it will be easier for you to recall that. So, okay, I sigma 2, I take outside. So you will be left with theta minus theta cube over 3 factorial plus theta 5 over 5 factorial, which will be nothing but sine theta. Now, just put the matrix structure 1, 0, 0, 1 cos theta plus I. What is sigma 2? 0 minus I 0 sine theta. Can you just multiply each term with cos theta for the identity? Multiply here, it comes with sine theta and I, and see what is the result you are getting.
R theta, sir.
So it is, okay, matrix wise, it will be first term cos theta. This term will be also cos theta. Then here you will get
Sine theta.
sine theta, and the one here you will get minus of sine theta. So remember the 2 cross 2 element which you just built by actually doing the rotation in that space. We wrote it x prime is equal to x cos theta plus y sine theta, so on and so forth. You did not need to do it now. You have got it just by knowing the structure. What is structure? The structure of SO2, the group structure is such that we are talking about matrices which are 2 by 2, they are orthogonal, they have determinant equal to 1. So if I think about it in this way, then the structure of this generator S prime will be such that it will turn out to be S prime will turn out to be skew symmetric, and it will turn out to be a traceless. The only most generic element 2 by 2 matrix having real terms is 0, 1, minus 1, 0. All other can be made just out of this one. And once you know this structure, you understand that your S, which is defined in terms of minus I S prime, is nothing but polyspin matrices. And that means that we have got now something rather interesting for SO2 group. SO2, which corresponds to 2 by 2 rotation in two-dimensional space, basically, that is generated by a polyspin matrix sigma 2. Knowing that it is generated by sigma 2 will allow me to study so many other properties of the group rather easily. In fact, R theta is now given. Let's say I would not have given you, S, and I would have given you R theta. So let's just do that also. Let's say in this problem itself, I would have given you R theta, which is written as cos theta, sine theta minus sine theta. And I ask you, can you find S? So what is the relation? S is equal to minus I dr over d theta with theta equal to 0. So can you do that? What will be dr by d theta? First element cos theta minus sin theta cos theta minus cos theta. Theta is equal to 0. What will happen? This will become 0, 1, minus 1, 0.
0.
Right? Now just multiply it by minus I. So S will become 0 minus I 0. Right? So you can generate your matrices just by knowing R theta also. It goes both the ways. So what I try to show you that just by knowing the structure of your group, you can figure out the structure of the generator, and from the structure of the generator, you can understand the group element. Or otherwise, knowing the group element will allow you to do the will allow you to find out the generator. So this is just the proof of principle of this Lie group, that SO2 is one group where you have studied that there exists one generator and we figured out something. The real application of this guy for the first time comes up in SO3. Now, do we know something about SO3 group? Do we know the order of the group?
3.
So
3.
3, and it is in real space, right? So can you think about what kind of now we will have generators we can think of in SO3 group? So all we need to think about is the generator and what those generators will be doing, nothing beyond that. How many parameters are there?
3.
What kind of parameters you can think of? Just make a close resemblance with SO3. Yesterday we discussed about it. How many angles? Three angles. So let me write theta 1, theta 2, theta 3. Where theta 1 you can think about rotation about x-axis. So it is the yz plane which is rotated. Theta 2 you can think about rotation about y-axis. So it is the xz plane where the rotation takes place. And theta 3 is rotation about z-axis where the rotation about xy plane takes place. And beyond that, you do not need to think about anything. And there lies, for each of the parameter, I do need to have one generator. So how many generators should be there in SO3 group?
3.
3.
3.
So I call them, okay, I have to call them something. So let me call it L1, L2, L3. You know why I call it L1, L2, L3. But right now at this point of time, they are just the generator. Generator means what? Remember that R delta theta now in three-dimensional space is written as I plus. Okay, now I have delta theta vector times L vector, or you can think about delta theta vector to be composed of delta theta 1, delta theta 2, delta theta 3, and L vector to be composed of L1, L2, L3, three components. So I plus delta theta 1 L1 plus delta theta 2 L2 plus delta theta 3 L3. Yeah. So if I want to write my R theta, what will be this?
Instead of I theta dot L.
So E raised to I theta dot L, and I can of course explicitly write it just so that you remember theta 1 L1 plus theta 2 L2 plus theta 3 L3. So it is the extension of what we have done basically. And this time I am going to study this group by first figuring out my R theta and then generating my L's from those R thetas. Fine. So let's just study R theta just like the way we found, since we already know cos theta kind of structures there. So let's just try to study and see what we can understand about L's, which are the generators. So generators, three generators for this one. Yeah. R, Z, theta 3. So I am interested in doing this. So what will be this kind of a structure? What kind of rotation I am talking about? I am talking about a rotation which takes place about this axis. Yeah, rz theta 3. This is the structure. So if there exists r, that vector will be changed to r prime. So x, y, z in three-dimensional will be changed to x prime, y prime, z prime on the application of this rotation about this z axis, which I call as the theta 3. Yeah. So can you tell me first what kind of matrix structure rz theta 3 will be having? 1 by 1, 2 by 2, 3 by 3, what kind of?
3/3.
3 by 3, because there is x y prime, y prime, z prime on the left hand side, and there is of course x y z on the right hand side. So this guy is a 3 by 3 matrix. Absolutely. Can you just tell me what kind of matrix will come out to be if I am doing this rotation about the z axis, so that x and y axis will start moving? So there will be angle. Yes. Can somebody help me
Cos
writing?
theta.
Cos
Cos
theta or cos theta 3?
theta 3.
Okay. Then next term,
Sin theta 3.
sin theta 3, and then next term
0.
0. Okay. Next row,
Minus sin theta 3.
minus sin theta 3,
Cos theta 3.
cos theta 3,
0.
0.
0, 0, 1.
Excellent. Excellent answer. Anybody else would say that they have understood how this was said? I mean, this is something which we have already done, to be honest, just that we were never writing z prime or z there. We did it in the two-dimensional space. Look into this x prime portion, the cos theta 3, sin theta 3, minus sin theta 3, cos theta 3. This is just rotating your x and y, and your z remains z, so that your z prime remains z, since the rotation is about the same. So this is something which helps you immediately find out your generator, right? I mean, your generator is what? Minus I times d of rz over d of theta 3 equal to 0. Can you give this thing? We did that. I mean, we have done it on the previous page. If you look into this, this is exactly what we did. So now that you have seen it, okay, can you help me writing down my L3 generator, which of course has to be 3 by 3 matrix? First term,
0.
Sir, 0
0. Second term,
minus I
third term,
0
0
next one, I
0 0
0
0 0 0.
0 0 0. Excellent. So you see that you have made the generator once you know the group element, and this is not any general generator. This generator has something interesting about it. What is the interesting thing about it? This is
Traceless.
traceless, right? And
Hermish.
Hermitian. You just look into it. Just like you got in the previous case that there was a traceless Hermitian in the previous case 2 by 2 matrix. In this case, you have got your first generator. Congratulations. Just by doing this simple relation, L3 is equal to minus I drz over d3. Okay, let's see if we can understand this further. I mean, this is rather simple now. So can I write? Can I write now R, let's say x theta 1? Can you help me writing out this? What
1.
kind? So 1,
0, 0. Cos theta 1. Sin theta 1.
yeah,
Minus sin theta 1.
since you said that, so I understood that you have understood it. Now that the rotation is about the x-axis, all I have to do is to do this, of course, transformation in the y and z, and rx theta 1 will have this structure. In fact, not only that, now you can even quickly write down this guy also, right? So 0 0 0 0 0. 0, 0, and then
minus I.
Minus iota.
minus iota, iota. And what kind of L1 this guy is? This guy is also 3 cross 3 Hermitian traceless. Okay, now I should give you Ry theta 2 also, just to make this guy complete. And there this thing looks interesting. Cos theta 2, 0. But you will find out that this guy turns out to be this minus sin theta 2. And here it will be sin theta 2. So 0, 0, 0. And there is some 1. Where should I write 1?
Middle term.
Which one I should remove?
Sir, middle.
Sir, second row,
Middle zero.
Which is the center. Yeah, right. And what should I write there?
1.
1.
1. Excellent. So can you also find out L2 that for me? L2 will turn out to be. So please look into this. Now only the thing which you'll have to remember, minus sin theta 2 is here. So this will be minus I or plus I on the first row, third element.
Plus I.
Plus I.
That is the only thing which you'll have to remember, and everything else is fine. So 0, 0, I, 0, 0, 0, minus I, 0, 0. Again, you will see the structure. Same. 3 cross 3, Hermitian, traceless. Now you got what? L1, L2, L3, which are nothing but the generators of L3. And I will say something further, that these three matrices which you have found in this, they are not just any three matrices. They enjoy certain other properties also very nicely. So for example, if you do any one of these, L1 and L2, you will get a result. This is a commutator bracket, which of course you have been using in quantum mechanics. The result of this will turn out to be I times L3. Please check. Homework. You can check it. Yeah. So L1, L2 minus L2, L1 should turn out to be I times L3, such that in fact Lj, Lk will turn out to be what? I epsilon j k. Okay, another L. Then L, this guy. This is the famous commutator algebra. Epsilon jkl is called
Sir,
Levi-Civita.
Levi-Civita symbol or tensor. And what property it enjoys? +1, -1, 0. Cyclic, anti-cyclic, any other.
Dummy.
Right? And this property is enjoyed by which operators? You remember, three operators enjoying this kind of property.
Angular.
This is where the angular momentum will be coming. In fact, not only that, I can ask you another homework, which will be L1 square. So you have got your L1 matrix, remember 3 by 3 matrix. I ask you to do square. L2 square plus L3 square, which should give you what? L square. Yeah. So do this and figure out what is the result which you are getting from this. And that will again be something which should correspond to your orbital angular momentum. In fact, again, because of the paucity of time, I do not want to. In the position representation, it can be seen that this operator can be represented by R operator cross K operator. I mean, remember that P is equal to H cross K, where momentum is given H cross K. So except for this H cross factor, which we are missing here, everything else about this operator is nothing but the orbital angular momentum operator. So from where these guys are now coming, think about it. Orbital angular momentum operator is coming out of this SO3 study of Lie group. SO3 study of the Lie group requires you to have three generators having the matrix representation, which is only one representation. There can be many representations, but having the matrix representation in the form in which we have got this traceless Hermitian 3 by 3 matrices, and all of these three will be such that they will result in the commutator bracket, the famous commutator bracket algebra, and also this L1 square plus L2 square plus L3 square equal to L square, and you will relate it with this. By the way, can you tell me in quantum mechanics what is the action of L square acting on any psi?
L into L plus 1 H
Yeah, there will be one h cross square.
cross
So right
square.
now I am just eating out that h cross square because that is okay. Some sort of units, no, natural units where h cross is equal to 1. But okay, so L square will be L into L plus 1. So if small l, there are orbital angular momentum L corresponding to three possible projections Lx, Ly, Lz. Then what is the value of small l? Three possible projections. When can it happen? L having three values, -1, 0, +1. So when is that possible? What is the value of small l?
1.
1.
One.
If you put l is equal to 1 here, what is the result which you will get here?
2.
2 by
2. So please check the result. I mean, it will be 2 times identity if it is 3 by 3 matrices, by the way. But okay, you will figure out. So do these homeworks which I have given you, and you will find out so one of this and another of this, and you will figure out that SO3 formalism or SO3 Lie formalism allows you to figure out these three generators L1, L2, and L3, or Lx, Ly, Lz in position representation quite naturally. There is nothing big deal. I mean, I didn't actually try to invoke any physics here, to be honest. I just invoked my group theory knowledge, and I got the results which are basically representing all the physics phenomena of SO3. So SO3, which is nothing but the rotation, proper rotation in three-dimensional space, since it leaves the length squared invariant, it basically forms a group of orthogonal 3 by 3 matrices. Choosing proper rotation only, which means the determinant equal to +1, that fixes the structure of the group. Once the structure of the group is fixed, I can now just study my generators like the way I have done it here. So today I have basically given you a very powerful portion of the studying continuous groups, where group theory shakes hands with physics, or you can say your quantum mechanics. Whole of the quantum mechanics which you did in your orbital angular momentum algebra, I mean, you did that by doing something that, okay, Lx is equal to r cross p, etc., etc. That L is equal to r cross p is nothing but the representation of an operator in position representation. I can keep on changing my basis, and I can keep on getting my operator in any other representation. So r cross p is the famous one. We can relate it. Again, guys who are interested, of course, they can write to me. They can read the Afghan portion where the angular momentum is shown to be equated with r cross p, so that it just gives you more feeling of L being represented by r cross p. I mean, remember that operators can be represented in any of the representation. So when you are taking the position representation where the basis functions are nothing but your position eigenfunctions, in that portion your r cross p is the famous representation of the orbital angular momentum operator. But in other basis vectors, this L will have some other representation. For example, the matrix representation which we have done in some basis space without even telling you what basis is. So there are so many things which we can do now with these L's, that, I mean, the whole orbital angular momentum operator algebra comes out of it. So at this point, I would like to take a pause. It is, of course, it takes time to sink in. In terms of group theory, it's pretty simple. All I said, just start with the idea, and the idea can change your life. Okay, Lee group idea has changed this life of studying our group elements in terms of generators, and generators themselves do something extraordinary. Generators generate spaces, so on and so forth. So those of you who are there with me today, I will request them to be there also with me tomorrow, because I will just show you how the same thing can be extended to my unitary space or the complex space, and we will have everything related with spin angular momentum. So those things come as the natural consequence of studying continuous groups in leaf formalism. Yeah, questions here, and then of course.
So all these things are only possible when our parameter goes to zero now.
No, that means that this group I is studied. So element is the infinitesimal rotation about the identity element. Remember that this is the basic. When theta equal to 0, what is happening? It is the identity element of that group, right? Right? What is theta equal to 0? Theta equal to 0 is identity element, right?
Yes, sir.
So that means all is happening that by studying the infinitesimal rotation about the identity element, you are able to study the group. You do not need to study any finite element, to be honest. You are just studying the infinitesimal transition or operation about this identity. So theta equal to 0 is nothing but studying my group about the identity element. And what kind of studying? It's an infinitesimal study. Du over d theta at theta equal to 0. Right? Du over d theta over theta equal to 0. It's a small tangent which you will build around this identity element or the group element. Right?
Yes.
Yeah, so that is the power of this theta equal to 0. Yeah, why theta equal to 0 is a very natural question. And what is about this theta equal to 0? So I am studying the whole group, not by studying my theta varying from 0 to 2 pi a, but I am just studying the group by studying theta equal to 0 and doing a very small variation around this. Why this variation is taking place? This is taking place because of the generator. So there exists a generator which generates this. Orbital angular momentum generates rotation in three-dimensional space. So when we are saying that L1, L2, L3 are the generators of theta 1, theta 2, theta 3, then what we are saying is that the generators are the orbital angular momentum. And what does it generate? It generates infinitesimal rotation as per the Lie group. So generator is the generator of that infinitesimal operation. Many powerful consequences. Linear momentum is something which we study. So how do we have a space translation, for example? So if a body is at rest, I want to translate in space, let's say in x direction only. What do I need to give? Body is at rest, I want it to move, space translation. क्या होगा इसका generator? You have to give it momentum. So momentum, linear momentum will be the generator of linear translation. So remember the conservation principles which you were telling me, that this whenever there is the invariance under space translation, linear momentum is conserved. When you say that there is this conservation under rotation, then there is this angular momentum is conserved. So what is happening there? It is basically it's the generators which are getting conserved there when something is happening. So generator of x is getting conserved there. Generator of theta is getting conserved in orbital angle. Can you think about now time translation? What do I need to give to have the time translation, not the space one? Generator of time. Energy. Exactly. Excellent answer. So these are all consequences of the group theory. I mean, it's just by studying my mathematical group structure, I can do that. Okay, too much in one lecture. So let me take a pause. Thank you guys. I will just upload the lecture. Just read it from your Afghan books together with the lecture which I am saying, and then see what are the questions which you are having on that. So mathematically, of course, everything is just I mean done on the board, but physically it is beautiful. It's excellent. Yeah, mind blowing. Bye, guys.